I don't know how long this will take. You may have time to do the homework today. I would say, although this is more of kind of like an algebra type thing that we're going to be doing today, it's pretty important for the unit overall to be able to solve these proportions. So it starts with a ratio. So it says a ratio of one number to another is a quotient when the first number is divided by the second. A ratio is usually expressed in simplest form. So if I'm looking at a similar figure and the ratio of one corresponding side to the other is 8 to 12, we could write that as 8 to 12, but it would be easier to use what ratio instead? What is 8/12 equal to? Or what is it reduced to, I should say?
2/3.
2/3, right. So if I have 8/12, then I want to reduce these ratios. It's going to give us smaller numbers to work with when we go to solve, if I can reduce them. And also our ratios could be written a few different ways. So it could be a fraction. Sometimes we use a colon, so like 2 to 3. Or we use words, 2 to 3. And we use this also at the end of the year when we do what's called a dilation. We take a shape and make it larger, take a shape and make it smaller, but in the same scale. Okay, that's our ratio. Now our denominator of a ratio, so it says of R to S. So if I have R over S, what number can I not divide by? What number can I never divide by? It gives me an error in the calculator.
0.
0, yeah. So our denominator cannot be 0, okay? Or S could never equal 0. We couldn't have a ratio where the number that I'm comparing to is 0. Okay, so this is it says quadrilateral. It looks like a trapezoid. We don't know for sure that it's a trapezoid. We know that it's a quadrilateral, which is that it has 4 sides. And so we also don't know that it's an isosceles trapezoid. I couldn't, for example, say that these sides are equal. We're not given any of that information. We just know that this is a 4-sided shape. What we can do is we can find the ratio of one side to another side. So the ratio of BC to AD, which means I'm going to go BC compared to AD as a fraction. What is the ratio there? So what is BC equal to? BC, side BC.
14.
14. And AD, which is over here, has a variable. So it's over 6B, that's fine. Now, so I can't do anything with that, but I can reduce the 14/6. So even though I have a variable, I could reduce this and divide by 2 and write it as 7 over 3B is the ratio from this side to that side. Or we could find the ratio between 2 angles. So this is a quadrilateral that's a little bit tricky here because it doesn't give me all of my angles. So I have 60, 70, 120, and then this one's kind of unknown. Does anyone remember what a quadrilateral has to add up to? It's 2 triangles in there. So 180 and 180 is going to give me 360. So I do need to make sure, so right now, smallest angle to largest angle, well, we know our smallest angle is 60, largest angle is 120, given what we have, but we do want to make sure that this angle wouldn't be one of those two. So we would do a real quick 120, 60, and 70. Those are the angles I have, which would give me 250. So if my quadrilateral adds up to 360, what would this angle have to be? 110. So we're good that this is the largest angle and that's the smallest angle. And what's important here is also the order. So I wouldn't go 120 over 60 because it doesn't say what's the ratio largest to smallest. It's saying what's the ratio smallest to largest? So smallest being 60, largest being 120. What is the ratio smallest to largest reduced? 1/2. Or we could say it's 1 to 2. Okay, or any version of what's up above. That's the ratio from the smallest angle to the largest angle. Another thing we need to consider, and it doesn't come up that much actually when we get to our geometry problems, but when we're looking at just our ratio and proportion today, if I'm going to express two quantities in a ratio, meaning I'm comparing them to each other, it has to be expressed in the same units. So for example, if I'm given a poster is 1 meter long and 52 centimeters wide, and it asks me to find the ratio of width to length, which means I want to go width to length in terms of how I'm going to set up that ratio. I can't find the ratio using two different units. So this is meters and this is centimeters. I can choose which units I use. So I could either go with, well, I'll make everything centimeters. So if I made everything centimeters, how many centimeters are there in a meter? Anyone know? It's 100 centimeters in a meter. 1 meter is 100 centimeters, which means that 52 centimeters is 0.52 meters, just so we have it kind of both ways. Probably would have been easier if we did feet, inches. You're more familiar with those American units. So if I'm going to find the ratio, I either need to use both centimeters, width to length, or I need to use both meters. So, and I also want to be careful here. It's tricky because it goes length, width, but then it asks for the ratio width to length. So what should be in my numerator here? 52 over, and if I'm going with centimeters, it has to be over 100. So I'd have.
Wait, would it be 152 or just 52?
52 over 100, so I have centimeters over centimeters. So I'm taking this with this, and then I could have taken this with this. Okay, because these are the same units, these are the same units. And then 52 over 100, I could reduce to 26. Oh, I could reduce even more than that to 13/25. Okay, or I could write it like this, or like this, 13/25. Okay, any version of that is fine. Now with meters on this particular one, it's a little trickier because again, I'll go width to length, and remember this is my width, and I end up with a decimal, so 0.52 over length of 1, and that's a little trickier. What we can do is say, well, 0.52 is 52 hundredths, and then I end up back where I was before. We haven't talked about that in a while. This is like a pre-algebra thing we talked about. This is in my tenths place, that's my hundredths place. So 0.52 is 52 hundredths because the decimal ends in the hundredths place. And then I'm here and I can reduce from there. Okay, so there's our ratio. Let's look at a couple geometry examples with this. So it doesn't have to just be two numbers that we compare. So when we're doing our ratios, it could be 3 or 4 or however many numbers we want to compare. We're just comparing numbers. So I could have A to B to C, or in words, I could say, well, A to B to C. And I could then break that ratio apart. So I could also say, if I have this, then A to C is the ratio of the first number to the last number. Or I could look at just A to B, which is the ratio, oops, of the first number and the second number. So if I'm given a ratio of several things, I can then break that apart and look at a ratio of just two of those pieces, if I wanted to. One way that you could see a ratio with three numbers, and I feel like this is a standardized test type question, it says the measures of three angles in a triangle are in the ratio of 2 to 2 to 5. Find the measure of each angle, which means if I have this triangle, okay, and I know a triangle equals 180, I know that these three angles are 2 to 2. So if I look at two angles, 2 to 2, which 2 to 2 would reduce to what? If I looked at just the first two numbers, 2 to 2 would reduce to 1 to 1, or those two angles must be the same angle, right? So I have two angles that are the same, or in other words, I'm looking at an isosceles triangle. Now I'm going to write that as 2x and 2x because we don't know what the actual value of these angles are. But whatever this angle is the same. And then my third angle, I should have drawn it a little better, would be 5, or in a ratio of 2 to 5 from here to here. And I could figure out what the measure of each angle is because I know that a triangle adds up to 180. So 2 to 2 to 5 has to add up to 180. And I could figure out what multiple that would be at for it to have this reduced ratio. So how many x's do I have altogether? 9 x's. And divide by 9 and x equals 20. If x equals 20, then what are my angles? What would this angle be? Two times 20?
40.
40. This angle would be 40 as well. And this angle would be 100. So if I had worked opposite here, this would have been an easier problem if we knew the angles and it asked us to find the ratio. If we knew the angles, then we would say, well, it's 40, 40, 100. If I were to write that ratio. And 40, 40, 100 reduces to 2 to 2 to 5. And you may have had a version in between where you're like, oh, they can be divided by 5, so that's 8, 8, 20. And then you're like, oh, that can be divided by 4, 2, 2, 5. So you could have built from here to get this ratio, or given this ratio, you have to figure out what multiple, what's x, and then you can find your angles. If that was confusing to you, don't stress too much. That is really not the focus of this unit. It's just kind of showing you where you would see this. Again, that's more of like a standardized test type question. Okay, so there's our basic ratio idea. Now we use this ratio idea to create what's called a proportion. And proportions are much more usable because it's something we can solve. A proportion is when we're saying two ratios are equal. Looks like this. Okay, or it could be this, but typically we see it in math class like this. And it's saying that A is to B as C is to D. A is to B as C is to D. That's my proportion. In my proportion, I have things called extremes and means. The extremes are the first and last term of the proportion. Those are my extremes. My means are the middle terms in the proportion. So on that first example, which looks like what we have up above, what are my extremes? Which letters?
Which example?
In this first example, A to B, C to D. The extremes are the first and last terms.
A and D.
A and D. A and D, these would be my extremes, and my means would be
B and C.
B and C. I have extremes and I have means. So then on the next example, my extremes would be 6 and 4.
Yeah.
Means aren't my inner numbers 8 and 3. Now, when it looks like a fraction equal to a fraction, let's actually rewrite that the other way around. So it could be 2 to 4 equals 1 to 2. Now tell me, what are the extremes? 2 and 2. I'm going to highlight it here though. And means 4 and 1. 1 and 4. And you'll notice that when it's a fraction, the extremes are across from each other and the means are across from each other. We're going to look at our middle example. In our middle example, if we multiply the extremes, what do we get? 6 times 4 equals 6 times 4 equals 24. If we multiply our extremes, we get 24. Extremes, the guys in yellow here. What if we multiply our means on that middle example? We also get 24. Means 8 times 3 equals 24. Is that also true on this example? If we multiply our extremes, which would be 2 and 2, we would get 4. We multiply our means, which are 1 and 4, we get 4. So what we can conclude is that the product, or multiplying the extremes, is equal to multiplying the means, or this is why cross multiplication works. And we did cross multiplication in algebra class. We are not going to look at a lot of proportions written this way. We are going to look at a lot of proportions written like these fractions. And so in general, we can say that A times D, going across here, multiplying A and D together, will be equivalent to multiplying B and C together. You can see how we rewrite our equation. I need this to like be zoomed in on. It's just hard to do with this guy. There we go. Okay, that it doesn't become a new fraction. That's the biggest issue I see students doing, is they like multiply and then make a new fraction where they have the top multiplication and the bottom multiplication. That's not what we're doing. We're multiplying A and D together. That's going to give me something, and it will equal what B and C multiplied together give me. Okay. So let's look at this, flip this page. And so this is going to kind of look different depending on what we have. So on example A, we just have a single term. So we want to solve for a variable using the fact that we know that these are proportions. And so because it's a proportion, we can cross multiply to solve. So for each of these, I have a variable somewhere in here. And I'm going to cross multiply to solve for that variable. And so what are my extremes here? What can I multiply together? A and 4. So here's my extremes. 4 times A is just going to give me 4A. And then I have my means, 16 times 5, which would give me 80. And now, because I've set 4 times A equal to 5 times 16, which is what cross multiplication allows us to do, now we just have an algebra equation, and I can divide by 4 and get A equals 20. Now, this is where students really mess this up. If I have more than one term, so like on B, I have 2 terms here. I have to be really careful about what that looks like algebraically. So I have x plus 2 be multiplied by 2. I have x plus 2, all of it be multiplied by 2. Okay, or I want to take those double terms. If I have more than one term, I want to put it in parentheses. And then in a minute, we'll distribute. And I have 5 times 6, 30. And I'll distribute that 2 through. So before I go to solve, I'm going to distribute and then solve from there. And it's still just an algebra equation, but I need to know how that works when I have more than one term. So that gives me 2x equals 26 and x equals 13. Okay. So I'm going to ask you to try C and D on your own. I will tell you that they are both fractions, so don't stress that they're not pretty answers like A and B are. You're going to get like a reduced fraction. For D, C is just going to be a fraction. Okay, but use that cross multiplication, see how you would set it up, and we'll compare answers in a minute. Okay. Should I do it? Should we distribute on that second one? So first one, I just kind of did a walkthrough and I saw 3y equals 20, which dividing by 3, just leave that as 20/3. Give you a minute to finish up D. Like hair inside my mask that will not leave. So on D, here would be the setup. So I have 13 times 6, which gives me what? Too far. 178, yeah. And then I have 3, and what I need to be careful of is it needs to multiply by that entire numerator, 2i plus 3. Okay, I can't just multiply it by 2i. I need to make sure that that 3 gets to everything that's in that numerator. Or if it was in the denominator, same deal. Doesn't matter where that double term is. Distributing 3 gives me 6y plus 9. And then subtracting 9, I get 6y equals 69. 6 does not go in evenly to that, but I would not leave that. What does that reduce to? What number goes into both of those terms? 3, and it's going to give me 23/2. Okay. Okay. So now you will definitely have time to finish your work today. But we want to look at just a few different properties that we use at times. Now, most of the time, like 99% of the time, we use that A over B equals C over D is equivalent to AD equals BC, or cross multiplication. Okay, like 99% of the time, that's what we care about, okay? But there are some other things that we could use. So cross multiplication, that's our first one right here. Okay, that's our first property. Other things that are kind of cool that are true and at times may be nice to employ. So let me give an example of this second one. So this took this first ratio, and what it did is it flipped it. It put C and B, it flipped it around. So just to give you an example, I'm going to write a proportion we know is true. So 2/3 equals 4/6. Now it's kind of cool to see that if I just do a little swap here, it's going to give me a different value. So if I put 4 here and 3 here, look at that. Are they still equal? Is 2/4 equal to 3/6? Yeah, it's 1/2. It's a different ratio. Okay, this is 2/3 and this reduces to 1/2, but flipping B and C still makes it true. Okay, that's kind of cool. I could also just flip the whole fraction. So meaning if I know 2/3 is equal to 4/6, then the reciprocal would also be true, or 3/2 would equal 6/4. And all I did there was flip A over B became B over A, C over D became D over C. Okay. That one's not, I don't think, as cool. I think that one should have been a little obvious. This one I think is kind of cool. So if I have, again, let's look at 2/3 equal to 4/6. What this property is saying is if I add another factor of my denominator, so if I add 3 on this side, right, that's B, so add the denominator of that side and add the denominator over here, which would be 6, it will still be proportional. So that's going to give me 5/3 equals 10/6. Changes the proportion, but they're still equal to each other. Okay, so just a few other properties that we see. Or if I know that several proportions are equal to each other, then adding all those numerators over adding all those denominators would also be proportional to them. It'd be the same reduced fraction. So this is kind of the trickiest part of our notes. We're going to decide which thing from up above, A, B, C, or D. We're not looking at 2 here, but A, B, C, or D, which one was used to change this original proportion. So here's my original proportion. What can I say that 5y is equal to? 5y would be equal to
2x.
x2 or 2x. Yeah, that is just my first property from up above. That's just cross multiplication. Okay, 5y must be equal to 2x. Then I have x plus y over y. So what I did there is I took this denominator and I added it in. What would that be equal to on the other side? What would 5/2 change? How would it change? That would be this last property. 5 plus,
Maybe 2x plus 5/2.
no. So what this one's doing is it's taking the denominator and it's adding a factor up top. So if I do the same thing over here, take my denominator and add it up top, or I could have written that that's equal to 7/2. Okay, that's property D. Okay, that if I add the denominator on one side, I can add the denominator on the other side and it would stay equal. What's happening here? So it took, now it says 2/5. Well, we don't have 2/5 here, we have 5/2. It flipped it. So what would 2/5 be equal to? Yx, I'd have to flip the other side. Exactly. And that one is which case? That's C, right? Let's see, just putting arrows to each example. Then it says x over 5. So what this one's done is it's taken this 5 and it's put it here. What would x over 5 be equal to? Y over 2. It's flipping the B and C around. That's property B from up above. Okay. Let's bring that over. Okay. So what you're going to do with your half hour, I guess we could do more today, but I don't want to get too far ahead. Is you're going to finish your homework for tonight, which is homework 31. You have this packet. Now I do want to just show you that, like, when you get to the end of it, you're going to have to distribute on both sides. So just be really careful in what you're doing here. So I think what I'll probably do is give you some work time, and I'll kind of start filling it in also myself, so we won't have to go over it tomorrow. And we'll look at these two together before the end, but just be really careful. If I have more than one term, use your notes to remember what that looks like, or I'll leave it up here. I need to make sure that I distribute to those double terms. And sometimes I distribute once, sometimes